As Georgia said, I'm not an expert in water environment, so I will try to do my best just to give you some introductions to satellite data and how this data can be used in veterinary application. I'm sure that many of you knows these pictures. This is the first Earthrise taken by Apollo 8 astronauts in 1968. And that has become an iconic view of our planet because it really explained the fragility of the Earth, the how fragile our system is in the middle of the space. And since then, I think we learned how to look at the Earth because we are on our planet, we are in our fields, we are in our activity, and we don't really see the immensity of what we can extract from our planet. Since then, a lot has been changed because we learned to look at the planet with different lenses to collect different informations, just to monitor our planet, to see and to investigate our resources on the planet, and of course this applies also to veterinary activities to be more general to the One Health approach, studying plants, animal, and human beings. A lot of satellites have been put in orbit since then. And I will just briefly introduce the Copernicus program, which is the European Commission program, in which there are sentinels orbiting around the Earth. And sentinels is not taken by chance as a name because sentinel monitor what is happening on the Earth planet. And usually they orbit around the Earth in twins, so to collect information more frequently. And they use different sensors, optical sensors and radar sensors, so they can get either optical information, like any kind of picture camera, or radar information. They can go through the clouds and get information. They use different bands, and the combination of different bands, which are physical properties of the Earth, we can identify some parameters on the Earth, like vegetation, like presence of water, like moisture. And this, of course, can be applied in my field of vector-borne diseases because you know that mosquitoes like water, like moisture, needs vegetation, and also on water environment. So mainly the satellite nowadays monitor oceans, land, and atmosphere. And they provide all this kind of information to give us as much as possible to monitor our planet. Um, Copernicus data data uh, gives information at 10 meters resolution. That means that from here to there, we have a square, and we can have information at this level of spatial resolution, which is a huge amount of information. But you can easily imagine that working with these images, one picture has 1 gigabyte of, of size. It's incredibly difficult, but they are also extremely powerful. This is an example. Not sure you can spot the algal blooms. They are more or less here. From satellite, you can see the green part of the phytoplankton activity. So you can really identify the status of our oceans. And here you see this is in North Adriatic Sea. And you can spot not only the green part, but also the white stripes that are mutual age. So this kind of information, this kind of data can be extremely useful to monitor where and when some events can affect our coast or our sea. And also with study or in-field activity, we can also associate with fish diseases or aquaculture issues. This is another example of how satellite can spot problems on our planet. This is was a sediment flow into the Tyrrhenian coast, the Tyrrhenian Sea, after 3 days of heavy rain in Rome. This is the Tiber River, and the sediment and the turbidity of the water was easily spotted by Sentinel-2 satellite. But of course, these are not just pictures. These are not simply beautiful images, at least to me, but they are sources of data. And now I think we have the duty of working with this data because a lot of investment has been made in the past by all the European space agencies, American, any kind of space agencies has produced this kind of data that now we need to turn into information somehow. And a quick overview of one application that we developed in our region. Again, this is a Sentinel-2 image, and we worked with the Environmental Protection Agency, Regional Protection Agency, and we went into the sea, in the sea through a boat using sensors, a multiparametric probe, collecting sample the exact day in which the satellite was passing over our place. So we could match the image and the parameter in field. The red spot here are a sort of transect in which we collected samples of pH, salinity, temperature, and also sample of water that was brought into the lab to look for turbidity. And there are many algorithms already developed which transform these images to this one with numerical value. And of course, it's not straightforward. You need to calibrate because every place, every location is different from the others. So that's why field activity is extremely necessary because you go in field, you collect your sample, you know the true value of what you're observing, and you compare with the satellite data and with the algorithm already existing. But this, of course, is an incredible additional value because from a few points you can extrapolate to your area, either in places where you don't have the samples or in different days because the satellite passes over the same place on Earth every 5 days. So every 5 days you can have the same image in the same place. So can you imagine how powerful this data can be? Now, well, my field, vector-borne diseases. We had a project funded by WOHA in North Africa. The objective was to better target surveillance for mosquitoes because, of course, they have no economic resources to go everywhere and sample mosquitoes or any kind of vector transmitting the diseases. So they asked us what we can do, how we can better target our surveillance. And we said, well, it's not easy, quite a huge extent, but satellite can help. So we decided to collect some satellite information and to identify ecoregions, which means to identify similar areas which share the similar conditions in terms of temperature, in terms of vegetation, in terms of rainfall. So once you have similar ecoregions in such a huge extent, you can say, wow, I got a specific virus here or a specific mosquitoes here. Where this ecoregion is present in other places, you select the other ecoregions, and you know that your surveillance might be targeted in that place. But again, it was not easy. North Africa seems to be quite a normal desertic area, but it's not. We have this kind of area in which you have river vegetation and desert. This is close to the Senegal. We have this environment, this is Tunis, where you have lagoon, ponds, town, and crops. We have the desert, but at the same time, you have in Morocco the Atlas Mountains with snow on the top of that. And the ecoregion doesn't want to be a selection of land use, wants to be a method to select similar areas in climate and environment. So even if two places are close, but they share completely different climate, they want to be part of the same ecoregion. This is the beautiful delta of Nile, which is green, extremely green because of the vegetation and the croplands that are there. This is another interesting landscape that you can find in Africa, where you have desert and then you have circle of crops. Because of the fossil water that comes up to the desert, and you can really have cultivation or crops of vegetation there. And from a vector-borne disease perspectives, of course, this is a perfect environment, might be a perfect environment because there is water, there is vegetation, so mosquitoes can be there. And this is another beautiful picture of a desertic area in Algeria. So the desert is not always the same. So, having this in mind, we needed to find a way to merge all these differences and find this ecological similar region, ecoclimatic similar region. And the Provna project worked on that. So we collect satellite data. Of course, the selection was tailored to data that are important for vector-borne diseases, for vectors itself. Temperature, day and night, water index, vegetation index, soil moisture, and rainfall. And this was done at 250 meter resolution. So impossible to do that at 10 meters resolution, of course, because at this extent we had to process 150 million pixels in each image that was merged by different images. But since we want also to catch the differences across the time, we worked with the 16 days temporal resolution. So we wanted to identify areas which were similar in a place, but also in time. So if I have 20 degrees in summer, I want to identify areas which also had 20 degrees in summer, not in other period of the year. This is extremely important because if I had to target my surveillance, I need to know where to go and when to do my field activities. It was not easy because what you need is not just a statistician. You don't need just an Earth observation expert. You need a multi-sectorial team to work with this kind of approach. Because you have to work a lot with the satellite data, but at the same time, you need to know which parameters you have to identify. So you need an entomologist that tells you, well, for this species is important this environmental variable or this climatic variable. Then you need engineers that put together all the process to select, to retrieve the data, to select the data, download the mosaic, etc. So the work is really incredible. And of course, being working with 150 million pixels, we need to work with some new methodologies that was actually an artificial, neural artificial intelligence approach. And the result was this one. Yesterday, we had an interesting conversation with some colleagues, and we spoke about the importance of giving a result to our stakeholders. And of course, if you go to the policymakers or if you go to the CVOs down there, you can say, wow, I have these fantastic artificial neural networks that select me ecoregions. So then you can go there. No, they won't understand you. But what we we try to do is give them also an association with the parameters in field. So we coded our result using an RGB classification, meaning that red is temperature, where the areas in which the temperature has the most impactful behavior. Green is where vegetation is more prominent. And green and blue and purple means more moisture or rainfall area. This because they can see, well, easily. You can see that everything is red. Desert. Temperature is the only variable because there is nothing. The signal from satellite is nothing. There is no vegetation. There is nothing. Only temperature can be. But what was amazing is that at that resolution, we could spot different situation in the middle of the desert. So we could identify different ecoregions. The one with the desert, and other one is green. So what do you expect we will find there? Oasis. So we could spot oasis, we could spot circle of crops, we could tell them, okay, if you need to make some surveillance, please go down there where there are variables, parameters, and factors that can affect vector-borne diseases. The method is not only spatial, is also temporal. So it means that you can monitor the differences in a place across the years. So if we run this methodology every year, we can see how the landscape changes, how the ecoregions changes. And down here, you see from 2018 to 2022, we had a change southwestern of the area. So it means that something was becoming more greener and greener, which is quite strange because we expect desertification almost everywhere. But we have to be aware that we also have some different pattern going on. And this was exactly the one that Sentinel-2 satellites caught across the years because there was an expansion of the agricultural areas. So the environment is changing, the factors are changing. So we need to pay attention of what is happening on the earth, because if we want to better target our surveillance, we need to monitor these situations in which climate and environmental are changing. So this is my conclusion. Uh, it is important, we have the data now. Everyone can access the data. They are completely free, available for everyone. What we need to do is to build up a strong team with different expertise to work with this data, which is of course different from the different domains, but we have the possibility to work on with such technologies nowadays. And it is important simply because they are frequent in time. We can adjust them from now to the next 20 years at least for Copernicus. So there is the availability to put in place services and applications that can last at least for for the time we are working on this aspect. So that's it. Thank you very much.